Okay, grade 11 chemistry. This is a very quick video to correct an assertion I made in my previous video. So this is a correction to video 1.2, where I used the term effective nuclear charge and I used it completely wrong. So effective nuclear charge is what we're trying to correct. Nuclear charge. And when I said effective nuclear charge, what I was really talking about was total electric force on the outside electrons, which effective nuclear charge is part of it, but the other part of it is distance. So the first thing I want to talk about is how the force on an electron, the electric force on the electron is going to be this, the effective nuclear charge, times the distance squared. Sorry, not times the distance squared. That'd be wrong. That means go up with distance divided by distance squared. Divided by distance squared. Proportional to, not equal to, but proportional to. There's other stuff to go into there. But yeah, it's distance is not actually part of effective charge. So what is effective charge actually in chemistry? Well, to talk about that, let's remind ourselves that look at the keep in mind. Look at the keep in mind up there. Opposite charges attract and like charges repel. So if we look at something like sodium with its 11 protons versus something like potassium with its 20 protons. Sorry, potassium doesn't have 20, it has 19. What am I talking about? Mr. B. I'm getting flustered. Alright, now sodium has 3 energy levels. 1, 2, 3. And 1 electron in the outer shell. 8 here. And 2 here. Potassium has 4 shells. Same kind of setup. Potassium has more of them. So as mentioned before, there's an attractive force towards the nucleus here, because the positives are going to attract the negative electrons. So there's an attractive force there, and there's also an attractive force here. But what I was missing when I was talking about effective nuclear charge was that there's also a repulsive force. There's a bunch of repulsive forces. This shell here is going to repel, and that shell is going to repel, right? That electron is going to feel a repulsion from any shells underneath it. Same thing here. This is going to feel a repulsion from any shell underneath it, because like charges repel. Now they're more spread out than the large concentration of positive charge in the nucleus, so there's less of a contribution, but it is a very important part of what makes an atom the size that it is and what kind of electronegativity you get. There's actually tables of this, so I'm going to actually pause and I'll find Wikipedia has a really good table of these, so I'm going to pull up the Wikipedia page. So I'm on the Wikipedia page for effective nuclear charge, and you can see here that hydrogen, just 1 electron, sees an effective nuclear charge of 1, so feels the whole proton. Now helium has 2 protons, but each of the electrons in helium only feels 1.6 effective nuclear charges, because they're repelling each other at the same time that they're being attracted to those positives in the nucleus, and so on and so forth. For lithium, you've got 2 shells, the 1s and the 2s, so The lower electrons actually do feel a little bit less than 3, but the outer ones are only feeling 1.2 effective charges. Right? Even though there's 3 protons there, the outer electrons are only feeling 1.2. And it goes on and on and on. It gets really crazy when we get down into stuff like rubidium, where it has 37 protons, but the outer electrons in that 5s shell are only feeling the effective charge of 5 of those 37 protons. Compare that to something like iodine, all the way on the other side, the outer electrons are feeling the effective charge of 11 of those protons. Because there's more protons, the charge isn't attenuated as much by all of the other electrons. So not only are there, there's less than twice the amount, right? 37 times 2 is 74, but the effective nuclear charge, the actual amount of attraction that they feel for the nucleus, is more than doubled, even though there's not twice the amount of protons in the nucleus. So effective nuclear charge is a big part of why the electronegativity goes up so much across a period. It's also a big reason why these are so much smaller than these, right? Because the effective nuclear charge is also going to say how far in those shells are pulled. So that's my quick correction. So please, keep that in mind. Thankfully, that specific definition isn't actually in the curriculum, so I'm going to keep the old video because I'm not about to remake a 40-minute video. But this is just to serve as giving you guys the real definition of it, just so that you guys don't use it in some other course and get confused and get a wrong answer at some point. Yeah, that was quick, so thanks a lot, and feel free to ask questions about this in class. Yeah, thank you very much. Bye.